Greetings to all those who have decided to view this particular documentary. This is a follow-up to a Zoom presentation which was entitled Some Tips on Counting, and that was the beginning of a series, and that was number 1. We now move on to number 2, and we continue our discussion on counting techniques that we began in that first documentary. So let's go straight to the topic itself. Much of this information was taken from the book called 1000 Olympiad Mathematics Problems, which I wrote earlier this year. And we are concentrating on lesson 3, which is entitled not Some Tips on Counting, but Counting, Probability, and Functions. So this is one section. In that section 3.3 up to 3.5 is what we are dealing with here. So those who want to have more information can please make reference to that section in that book. Okay, let's begin straight away with the question. In how many ways can n different objects be rearranged? So this is really the question. In how many ways can n different objects be rearranged? What this means is that if I look at, say, 6 objects like this, and you got the objects, you can call them, you can name them anyhow you like. Suppose we name them as A, B, C, D, E, and F. And then we want to arrange these 6 objects. Well, in how many ways can they be arranged? Now, by arrangement, we mean, like, for instance, I could have rewritten like this as D, C, A, B, F, E. I could have said that, and this is a rearrangement of the original 5 objects. These objects, we are naming them like this. It could be any objects. And so we want to know how many possible ways which are there in which they can be arranged. Now, if we follow through from the first lesson on this, the answer is that the first object can be chosen in 6 different ways. We want a rearrangement, so the next object cannot be the first object. So it can be chosen from only 5 different objects, right? So we put down how many ways can the second object be put in. Now these 2 have been chosen, and we want a rearrangement of this. So it follows that there are only 4 left. And likewise, if you continue this, you have that each box can be filled in so many ways. And then from this point onwards, we apply the second counting principle, which says that the number of ways is you have to multiply all these numbers. That's the second counting principle. So therefore, the total number of ways, number of rearrangements is 6 times 4 times 4 times 3 times 2 times 1. You multiply all the different possibilities, and that is the same as 1 times 2 times 3 times 4 times 5 times 6 if you write it backwards, which by definition is 6 factorial. 6 factorial can be written in either way. So that's the answer to this question if you had 6 objects. So in the same way, the number of ways of arranging n different objects will be n factorial. The same argument works. The same argument works. All right. So if we want to actually use n instead of 6, we could have started off by saying that the first object can be chosen in n ways, the second in n minus 1, and the third in n minus 2, and so on, until you come to 1 at the end. And if you multiply all these things together with the number of ways, number of rearrangements, is equal to n into n minus 1 into n minus 2, all the way up to 3 times 2 times 1, which is nothing else but n factorial. If you read it backwards, it's 1 times 2 times 3, all the way up to n. So that is the explanation for this important statement. Okay. So if we want to, let's just go on. Okay, this exercise here, find the numerical values of each of the following without the use of a calculator. The calculator will allow you to find 5 factorial, for instance, but it would not allow you to find 100 factorials because this number is too big for a calculator to handle. So we want to find out some methods of actually solving, to simplify these things without using the calculator. With 5 factorial, well, we simply have to multiply 1 times 2 times 3 times 4 times 5, and you can do this in any way you like, and you'll get the answer 120. Okay, that is straightforward. But now if you want to look at 100 factorial over 98 factorial, okay, so the way to do this is, well, let's expand this whole thing. So let's expand this and see what happens. The top part is 1 times 2 times 3, all the way up to times 100. And the bottom is 1 times 2 times 3, all the way up to 98. Okay, now you'll see that many terms cancel here. The 1s cancel, the 2s cancel, the 3s cancel, and so on. And 98 of the top numbers will cancel. All the numbers from 1 to 98. 98 would cancel the 98 there. And the only things which are left is 99 times 100. And that is easy. That's 99 with 200 zeros placed behind it. So that's 9,900. All right. Now this one here is almost similar, but very similar to that. It's just that it's got an extra factorial underneath it. So what is this? This is let me see. Sorry, I'm just trying to, okay, let's just do it here on the side. I'm looking for some space here to write. I don't think that's a problem. So here, the 16 factorial over this, if you rewrite this thing out, what it involves is, this is 1 times 2 times 3, all the way up to, I'm going to put down 14 times 15 times 16, yeah. And then at the bottom, I'm going to put 13 factorial, 1 times 2 times 3, all the way up to 13. And then you also have 1 times 2 times 3, because you got 3 factorial as well. And now we can see why I went up to 14, because all these things cancel. The only survivors are 14, 15, and 16. So I just want to emphasize that this thing here is equal to 16 times 15 times 14 divided by 1 times 2 times 3. So you start from 16 and you go only 3 steps down, and then you write down 1 times 2 times 3 in a thing like this. You do this because of the fact that 13 plus 3 is 16, but we'll come back to this some other time to illustrate this. So when you work this thing out, now you can cancel. You don't have to multiply all these things out. 3 goes into 15 5 times, 2 goes into 14 7 times, and you simply have to multiply 16 times 5, which is 80, and that times 7 is 560. So this is just to give you some practice on working with factorials, that you can do a lot of cancelling when you're working with factorials, which are in the form of fractions. All right, so let's just get on to the next one. So here's another problem. It says, prove that 100 factorial over 2 to the power 50 times 50 factorial is the product of the first 50 odd numbers. Okay, now that looks like quite a difficult problem. So let's go for it. So let's write down the left-hand side is 100 factorial over 2 to the power of 50 times 50 factorial. Okay, so what do you have here? You have that if I expand the numerator, I'm going to get 1 times 2 times 3 times 4 times 5 and so on. I'm going to put quite a few of these numbers and go up to 100. And here, 2 to the 50, okay, we wouldn't try to expand that. We know this is 2 multiplied by itself 50 times. But the other one we'll write down 1 times 2 times 3. Finishes off at 50. Now, what I'm going to do is I'm going to start cancelling the 2's here. There are quite a lot of 2's here, right? Now, you'll see that the number of even numbers in the first 100 numbers 2, 4, 6 up to 100, there are half of them are even numbers. So there are 50 even numbers here. So what I'm going to do is I'm going to take those 50 even numbers and divide each one of them by 2. You see? Because even numbers, 2 goes exactly into that. So what I'm going to do is I'm going to eliminate this 2 to the power 50, 2 times 2 times 2, 50 times, by cancelling those 52s with those numbers at the top there. So let's do that. So what happens is, so to that end, let's just rewrite this this top part. So we separate the even numbers from the odd numbers. We'll take out the odd numbers from there, and if you just remove the odd numbers from the top, you get 1 times 3 times 5 all the way times 99. I'm separating them because I'm planning to cancel the 2's from the even numbers. So let's put all the even numbers together so I can keep track of them. And then at the bottom, I've got 1 times 2 times 3 times 50. And I also have 2 to the power of 50 here. Okay, so okay, sorry about that bit of untidiness there. So now here you will see that when the 2 to the power of 50, I'm going to take out all the 2's from the top there. And what am I left with? What I'm left with, some of you would see this thing straight away, but let me just do it in full in any case. So you get all these odd numbers, 1 times 3 times 5, going all the way up to 99. If you take out all the 2's, the 52's from here, you'll have 2 to the power of 50. There are 52's. And what are you left with? You're left with 1 times 2 times 3, all the way up to 50. Because the 2 cancels with that, you get 1. The 2 cancels with that, you get the second 2. And then the 2 cancels with that, you get 3. And 2 cancels with that, you get 50. So that's what you got. And you will see that this is the same as what we got at the bottom. The 2 to the 50 and all these cancel, and you are left with, you're left with 1 times 3 times 5 all the way up to 99, which is equal to the product of the first 50 odd numbers, as you can see, right? So you can see this is a product. It's all being multiplied. All of them are odd, and there are 50 of them, of the first 50 odd numbers. Okay, so that is the solution to that problem. Right, it was, as you can see, it was a fairly challenging problem. So at your own time, you can go over it again to understand it, but it would be nice for you to try it out on your own to see whether you can get this and then check the solution. Always do that. Okay, I want to move on to the next problem. 8 books are to be arranged on a shelf. In how many ways can they be arranged? Well, we just said that if you got n objects, the number of ways in which they can be arranged or rearranged is n factorial. So in this case, you got 8 books are to be rearranged, and so therefore the answer straight away is 8 factorial. I'm not going to go through the logic of this because this is like a thing that you need to know, that if you got n objects and they are rearranged, the number of ways to rearrange them is n factorial. So we can go straight to the answer in this problem. Okay, so let's just go down. How many 5-letter words with no letters repeated can be made using the letters of the word plain? So to make a 5-letter word, you have to rearrange these 5 symbols. So this is exactly like the same problem that we had before. There we had books on a shelf. Here you've got letters in a word, and therefore the number of ways which can rearrange all these 5 letters is again the total number of rearrangements of 5 objects. The number of ways to rearrange 5 objects is 5 factorial. So once again, we don't have to go into any long discussion on that. Answer is 5 factorial. Now, here we have this question. How many 5-letter words can be made using the letters of the word plain if repetitions are allowed? Now, here, this is not a rearrangement anymore. It is you can repeat words, you can repeat letters. So you can have like P, 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 5 Ps. Right? No, that's not a rearrangement. So now we have to argue this in a different way. We can't use that formula anymore. So once again, we do what we always do. We draw our 5 boxes. 5 boxes because you are making 5-letter words, and then each letter has to be chosen to create this 5-letter word, and repetitions are allowed. So you use the logic or the argument. The first letter can be chosen in 5 ways. Now here, this is where this thing changes. The second letter can be chosen. Unlike before, we said 4. The reason was we're not allowed to choose the first letter. We only got 4 left. Now we are allowing repetitions, so that constraint falls away. So here, the second letter can also be chosen in 5 ways. And likewise, the third letter can be chosen in 5 ways. Every letter can be chosen in 5 ways because repetitions are allowed, right? So by the second counting principle, right, the number of ways this can be done is 5. After this has been done, this can be done in 5 ways and so on. This says that the answer is make this the correct subject, the number of words is equal to 5 times 5 times 5 times 5 times 5, which is 5 to the power of 5. And that, if you work it out, is 3,125. Yes, you can make many more words. Before we saw that if repetitions were allowed, it'll be not allowed, then it's 5 factorial. And that we saw earlier on, 120. So here, if repetitions are allowed, you've got many, many more words, 3,125, right? So that's an interesting observation. Okay, let's get on to the next the next question. Here you got 9 books have to be arranged on a shelf, 4 of which are history books, or books on history, and the remaining 5 on geography. Now, if the history books have to be together, 4 of them, that is, they are not to be separated, how many arrangements are possible altogether? So this is a slightly different kind of a problem. Let's just understand it. It says that the history books have to be together. And there are 4 history books and 5 geography books. So I've actually drawn the 9 slots here, where the books will be sitting on the shelf. And so we want to, for example, we will have a thing like this. You're going to have the 4 history books, say here. Say H for history, for example. And then the geography books will have to be the remaining places. Nothing is said about how the geography books are to be placed, only about the history books. So now the question is now, how many such arrangements are there? Now here, we first have to think of the history books as being together. Suppose you sort of bind them and you can regard them as a single book. As a single book. Then you can think of these as being 6 books instead of 5 books. But maybe that might not be the best way to go. Maybe it might be better to see how many ways can the history books be placed. You can have the history books. Firstly, you can work it out as if you regard the books together. But let's do it like this first. First, the history books can be placed in 6 ways. Well, let's see. You can put the 4 here, the 4 history books there. This is a start. Or you can put the 4 next to each other here. Or starting here, starting here, starting here, starting here. But this is the only place you can go up to. Because from this point onwards, if you've got the 4 history books, you filled up the shelf. Right? So they can be placed in 1, 2, 3, 4, 5, 6. Yeah, that was right. It can be placed in 6 positions. Right. Fix their position. And count. In this case. All right, so suppose I fix this. Right? So, in other words, the history books occupy the 4th, 5th, 6th, and 7th places. All right. Now, how many ways can these books be arranged? Well, in that position, the history books can be arranged in 4 factorial ways. Call them H books. In 4 factorial ways. Because you can turn them around anyhow you like. They are different history books, so the arrangement is very important. Right? They're not all the same. So they can be arranged in their own way. All right, so once you take, for each of these arrangements, factorial arrangements. In other words, I'm fixing a particular arrangement. Now the geography books can be arranged by themselves now. There are 5 of them. They can be arranged in 5 factorial ways. There are 5 factorial arrangements of the geography books. Right. So for this position, of the H books, which was fixed, there are 4 factorial times 5 factorial arrangements. Oh, then you have to work this thing out. Okay, you can use a calculator for that. I think you get 24 times 120. So that's 2880 arrangements. All right, but now that doesn't stop there. The final answer is because for that particular arrangement, you got so many possibilities, but there are 6 such positions for the history books. So for each one of those, there are 2,880 arrangements, and therefore, altogether, you'll have 6 times that number of arrangements. So that, if you multiply that out, you get 17,280. So that's the answer to this question. All right? It's a little demanding because you have to logically argue. There are 3 stages to this. The history books can be placed in a certain place, and they can be arranged by themselves, and the remaining ones can be arranged by themselves. So there are 3 different scenarios here. Okay, so that is the answer to that question. Let me proceed. Sorry, I'm having difficulty with this mouse. Oh goodness. All right. Sorry about that. Okay, now you've got 4 books are randomly selected from 7 different books and are arranged on a shelf. How many arrangements are there altogether? And again, this we've seen. So the first book can be chosen in 7 ways. You want 4 books, right? And there are 7 books altogether. So you have to choose the first book, and they are randomly selected. There are 7 different books. So the second one, once this position has been fixed, the second one can be chosen in 6 ways. So that's the answer. The answer is a product of all these, and that we can work out to be something. It was 42 times 20, which I think is 840. All right, so this is not so difficult to see. But what I want you to notice is that you can write this thing here in terms of factorials. The product of 4 consecutive numbers can be written in terms of factorials. What do you mean by that? What I mean is that I can complete this product, by which I mean I keep multiplying it until it comes to 1. 7 times 6 times 4. And suppose I keep multiplying this thing until I come down to 1. In other words, I'm going to stick in a 3 and a 2 and a 1 here. Right? Now these guys weren't there before, so you're not allowed to bring it in like that unless you divide by the same number. Then these two numbers are the same. So once we do that, then you can see now that this is the same as the top now is 7 factorial. And here you have 3 factorial. But observe that 3 factorial is, the 3 is nothing else but 7 minus 4. That's where it actually came from. Right? Because there were 7 numbers altogether. If you take 4 away from there, you're left with 3. So the answer to this question, 4 books are randomly selected from 7 different books and arranged on a shelf. How many arrangements are there altogether? The answer is 7 factorial over, you got 4 books, over 7 minus 4 factorial. So that gives us an idea. If I had, for instance, 8 books are randomly selected from 15 different books, then I can use the same principle to say that the answer will be 15 factorial over 15 minus 8. So in this case here, you're not rearranging all the 7 different books. You're only arranging 4 books. You take 4 books from there, from the 7. You're picking a certain collection, certain number of books from a large number of books, and you are rearranging them, right? Or arranging them, if you like. And the question is, how many such arrangements are there? So what we are going to do is try to say, let's get to the next. I keep having problems with this. Sorry. All right, so what we wanted to do is the number of ways of arranging n objects taken are at a time. The last example illustrated this. I'm arranging 7 objects, but I'm taking them 4 at a time. I'm actually arranging 4 objects, but you say it like this. The number of ways of arranging 7 objects taken 4 at a time is this n factorial over n minus r factorial. See? Now, this is the same as 7 times 6 times 5 times 4, which we had before. And then we said it's this. Now, you see, this is a product starting from 7 and landing at some strange number here. So you want to know where this thing came from. If you want to know about that, you will, we can see where it came from You just have to think about it a little bit, and you will see what actually happened is, if I wanted to find out sorry. Okay, sorry, I am having some problems with this mouse. Oh my goodness. Okay, let's just go, all right. Oh, I'm sorry about that. Okay, so what we want to know is, you're taking R objects at a time. So in other words, there are R objects here altogether. The number of things here is R, because you're filling in boxes and there are slots, right? And you're starting with n and n minus 1, we're landing up. So there are altogether. And this last number, we don't know what this last number is. Suppose if I call this x, right? Then we saw earlier on, this is R, that if you're starting product, you've got consecutive numbers, starting from x, this is a smaller number, and going all the way up to n, how many numbers are there? So if you start from x and you go all the way up to n, like for instance, if you're starting from 26 and go all the way up to 50, how many numbers are there? We said it was 50 minus 26 plus 1, right? That's the method. So here you got the n numbers here altogether. I'm sorry, the r numbers, but it starts from x and ends at 1. So the number of numbers is n minus x plus 1. And that number is already equal to r. And that's how, if you solve for x, you will see you got n minus r plus 1. I wanted to know what the last number here is. Okay, but you don't have to worry about that. All we have to do is to just say, you keep starting from n, you keep going until you come to r objects. And in practice, you don't need this formula. And in practice, formula is not used. This is quite important to know. You must argue it out by saying the first is filled in n ways, the second is n minus 1 ways, and so on. Okay. So an arrangement, instead of using the word arrangement, one can use the word permutations. The word permutation means, it's another word for arrangement. See? So let's just go to that one. First, I just want to save this thing. I'm sorry, it takes a while to move the slide here. So the word permutation is often used to denote an arrangement. They are synonyms. So sometimes we say instead of the number of arrangements of n objects taken r at a time, you speak about the number of permutations of n objects taken r at a time. And we saw that the number of such arrangements is n factorial over n minus r factorial. This should have been factorial here. All right, so this is r factorial here, so n minus r factorial. Just please correct that. Okay, let's just move on because this took an unnecessarily long time. And we want to get on to the next slide to see where we are going. So we got some problems here. How many five-letter words have exactly one vowel? Or how many five-letter words having exactly one vowel are there? All right, let's try this problem. Now, this is a slightly different problem. It's got exactly one vowel. So how do we do this? So we want to have five-letter words. Pardon the untidiness of this diagram. But all these diagrams have to have exactly one vowel. So suppose I choose a vowel here. Now, if I choose a vowel here, I've got five choices, A, E, I, O, U. So suppose I choose A here as my vowel. Right. So now, in how many ways how many words are like that, where A is here? Well, you've got 25 letters to choose from because you need to have, exactly one vowel. So you've got 26 letters of the alphabet. So you must remove the 5 vowels, right? So you're going to choose 4 vowels from 21. I mean 4 letters from 21. You're not allowed to choose A anymore. So it'll be, the first one can be chosen in 21 ways, the next one in 20 ways, the next one 19, the next one 18. So there are that number of ways of choosing if you have the letter A. Now, instead of A in this position, if you had any of the other vowels, A, E, I, O, U, right, then what happens? Then in that case, the number of possibilities would then be so there are 5 here now. Because you could for each one of these there are that number, but now you can choose this first letter in 5 ways, and then you still have 21, 20, 19, 18. For each choice of the vowels there are this number of words. There are 5 choices of the vowel, so there are that number of words. All right, so we are at this stage now. So the number of words is 5 times 21 times 20 times 19 times 18. But then that happened when A was here, where that one vowel was occupying the first position. Then you have the situation. See? But now that one vowel could have occupied the second position. You could have had the A. I could have had the A instead of the first position, I could have had it in the second position, or the third position, or the fourth position. So there are different positions that A could have occupied. See, A could be here, or the wall could be here, or the wall could be here, or the wall could be here. So there are 5 different positions in which the wall could have occupied, right? So we have to multiply this thing here by 5. So this was for the first position. You have this, and for this, but there are 5 possible positions. So this is the answer to the problem. The number of 5-lettered words having exactly one vowel is this one. So one has to use a calculator to work this thing out. I don't know what the answer is. And I think it's going to be 3, 5, 9, 1, something like that. Okay, but I'm not sure. Okay, now, so that is the solution to that problem. Let's see what the next problem is. So I'm back at the same problem here. Oh, I seem to have mastered this thing. Now, in how many ways can 2 objects be chosen from n objects? Now, this is a very, very important problem. There are many, many examples to illustrate this. I don't have much time, so I'm going to first say, in how many ways can you choose 2 objects from n objects? The way to actually answer that question is by actually constructing 2 objects from n objects. And what I do here is I call those n objects 1, 2, up to n. Right? It could be A, B, C, D, or whatever, but 1, 2, up to n is a very convenient way of doing this thing. So to list all the sets having 2 objects, what do? I say, okay, let me start with 1, 2, 1, 3, 1, 4, and go all the way up to 1n. I insist that 1 is in that pair of 2 objects that I choose, right? I insist that 1 is there. And you see that if you count the number of pairs with 1 in it, you'll see that there are n minus 1 of them. All right, now I insist that 2 is in that pair. I've already counted it with 1, so I don't have to count 2 with 1 anymore. I have to count it with 3 and so on, right? And that way you're missing 2, both 1 and 2, from that list of n objects, so the n minus 2 of them. So if you keep going down like this, now you say insist that 3 is there, and go on until you insist that n minus 1 is there. And when you come to that last one, there is only 1. So if you want to count the total number of pairs altogether, you have to count the total number that we've written down here. Now we saw that here there were n minus 1 of them, here there were n minus 2 of them, here there are n minus 3 and so on, and in the last one is only 1. So if you want to count how many pairs you've got, you simply have to count 1, 2, 3 up to n minus 1. Okay, so this is what we got. So you will count 1 plus 2 plus 3 plus 4 up to n minus 1. And here we know how to add the first n natural numbers. It's n into n plus 1 divided by 2. But you got n minus 1, so it's n minus 1 times the next one, which is n, divided by 2. So this is a very important formula. Let's just summarize why we did this. I went through this in quite briskly, but you have the screen so you can have a look at it. So a set having n elements has, that's the one, n into n minus 1 over 2 element subsets, right? For instance, if I had if I had 10 elements, right, and I want to work out how many 2-element subsets does a set having 10 have, then it's going to be 10 times 9 n into n minus 1 divided by 2. And then you can cancel. So there are 45 2-element subsets from n elements. Now, you might ask, where did I get subsets from? But what we are saying is that we are choosing 2 elements from n elements. So in effect, we've got a set having n elements, and we are choosing 2-element subsets. The way we looked at the last example, you saw that they had curly brackets around them because we were choosing 2-element subsets. All right. So there are some very interesting problems associated with this, and let's just have a look at some of those problems. The first one is this one. "11 points are selected on a straight line." It's the kind of problem that occurred some time ago in an Olympiad problem exam. 11 problems are chosen on a straight line. These, if you count the number of points here, there are 11. And the 12th point is chosen outside the line. This is the 12th point. And all this point here is joined to all these. Now the question is, how many triangles are there in the diagram? Now that's a very interesting question. How many triangles are there? Now you can start counting the triangles. Say, okay, the 1 here, the 1 here, and 1 here, and so on. But I can show you that by the time you get to the answer, it will be so complicated you wouldn't know whether you've counted a triangle or you didn't count it, and so on. It will be very, very complicated. But if you use logic and retranslate this problem into a slightly different language, you will see the answer is very, very easy. Right, let's analyze this. You want to find how many triangles there are in this picture. All the triangles have got one point in common. This point is already there in the triangle. So I need to find 2 other points to complete the triangle. Those 2 points are chosen randomly from this lot. Every time I choose 2 points, like that and that, then I have a triangle. Like that. If I chose that and that, for instance, then I have this triangle going all the way up to this, going up and coming down. So the number of triangles is exactly the same as the number of ways in which you choose 2 points from 11 points. I'll repeat that. The number of triangles, one point is already fixed. You need to choose 2 other points. So the number of triangles is the number of ways in which you can choose 2 points from 11 points. And the answer lies in the previous question. We said to choose 2 points from n points, the number of ways is 11 n into n minus 1, 11 times 10 divided by 2. So there are 55 triangles. So without even drawing a triangle, without counting it manually, you can get the answer. So this is a very, very powerful method of counting, you would agree. Okay? There are other examples, like for instance now, there were 50 people attended a party. If each of them shook hands with every other person exactly once, how many handshakes were there? So this is another context, right? But it's the same principle. Because what is happening here? You've got 50 people and you want to count handshakes. So what do you mean by a handshake? A handshake is always between 2 people. A person can't shake hands with himself. You can't shake hands at with one handshake with two different people, right? I can only use one hand at a time. So you have, so the number of handshakes, and each handshake is associated with two people. So you want to count the number of handshakes, you want to count the number of ways in which two people can be selected from 50 people. See? The number of ways in which two people, because every time you have a pair chosen, then you have a handshake, right? Two people, they have to shake hands. And every time there's a handshake, there are two people involved. So the total number of handshakes is equal to the number of ways of selecting sorry for the bad writing, selecting two people from 50. And that we know that answer. That is equal to 50 times 49. 49 divided by 2. So n into n minus 1 divided by 2 tells you the number of ways that two people can be selected from 50 people. So then this, I would do it like this. I'll cancel the 25, multiply 49 by 25, I divide by 4, by 12, the remainder is 1, I'll put 25 then. Okay, so that is the answer to that question. Okay, so I've finished my hour, so I'm going to call it a day here, because each of these takes just over an hour long. And so that takes care of some tips on counting. And the next time we meet, we will proceed with the third version of this. There will be, I think, only 3 different parts in this series of talks about counting. And be sure you listen in to the third talk on this. That will be some tips on counting 3. Bye and enjoy the rest of your day.